March 19, 1942. A cramped office in Aberdeen Proving Ground, Maryland. The meeting lasted 18 minutes, but those 18 minutes would birth America's deadliest armored weapon. Major General Jacob Devers slid 3 photographs across a worn oak desk. Smoking American tank hulls in Tunisia. "Our Shermans are dying," he said flatly. The man across from him, civilian engineer Thomas Harwell, studied the images with mounting dread. His hands trembled slightly. 6 months earlier, the Army had rejected his tank destroyer design as impractical and unnecessarily complex. Now, Devers asked a question that seemed desperate. Can you make it work? Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The photographs told a brutal story. In North Africa, German Panzer IV and Tiger tanks were systematically destroying American armored units. The Sherman, America's frontline medium tank, mounted a 75mm gun that could barely penetrate German frontal armor at combat ranges. Meanwhile, the German 88mm gun could destroy a Sherman at 2,000 yards, often before American crews even knew they were under fire. The mathematics of survival were grim. Intelligence reports indicated that it took an average of 5 Sherman tanks to destroy a single German Panther. The casualty ratio was unsustainable. At current loss rates, American armor divisions would be combat ineffective within 6 months of sustained engagement. The Army's existing solution was the M10 tank destroyer, a Sherman chassis with an open-top turret mounting a 3-inch gun. It was better than nothing, but barely. The M10 was slow, lightly armored, and its guns still struggled against the newest German armor. Production had begun in September 1942, but field reports were already questioning its effectiveness. Traditional military doctrine held that tank destroyers should be lightly armored, highly mobile vehicles designed to ambush enemy tanks from concealed positions. The theory assumed that speed and positioning would compensate for thin armor. Combat reality was proving this doctrine fatally flawed. German tanks didn't obligingly drive into ambushes. They advanced with infantry support, artillery coordination, and air cover. American tank destroyers needed to engage under conditions far more chaotic than doctrine anticipated. Thomas Harwell had understood this problem 6 months earlier. His rejected design proposal had called for something the Army considered contradictory: a heavily armored, powerfully armed tank destroyer. The Ordnance Department's rejection letter, which Harwell kept in his desk drawer, had been blunt. The proposed vehicle violates established tank destroyer doctrine. The excessive armor weight would compromise mobility. The proposed gun exceeds practical mounting parameters. The design is rejected as fundamentally unsound. But Harwell had seen what others hadn't. He'd studied reports from the Eastern Front, where Soviet and German forces were engaged in the largest armored battles in history. The Soviets weren't using lightly armored tank destroyers. They were mounting massive guns on heavily armored chassis. The German Ferdinand, mounting an 88mm gun behind 200mm of frontal armor, was virtually indestructible from the front. Harwell had proposed an American equivalent, a low-profile armored fighting vehicle mounting the largest gun that could physically fit, protected by sloped armor thick enough to survive frontal engagement. His calculations showed it was possible to create a vehicle weighing under 40 tons that could mount a 90mm gun, the most powerful anti-tank weapon in the American arsenal, behind armor that would stop anything the Germans could fire at combat range. The Army had rejected it because it didn't fit their doctrine. Now, with American tanks burning in the North African desert, doctrine was being rewritten in blood. Devers needed a solution, and he needed it in months, not years. The question wasn't whether Hartwell's design was orthodox. The question was whether it could be built in time to matter. Harwell didn't answer immediately. Instead, he asked Devers a question that would change everything. What if we stopped thinking about tank destroyers as light cavalry and started thinking about them as mobile fortresses? The concept violated every principle the Army's Tank Destroyer Command had established. Their doctrine, codified in field manuals and training programs, emphasized speed and maneuverability over protection. Tank destroyers were supposed to be hunters, fast, agile, striking from ambush and withdrawing before enemy guns could respond. But Harwell had spent 3 months studying actual combat reports, not theoretical doctrine. He'd obtained after-action reviews from North Africa through a contact at the War Department. The reports painted a consistent picture. American tank destroyer crews were dying not in high-speed chases, but in direct firefights where their thin armor was a death sentence. "Look at how tank destroyers actually fight," Harwell said, spreading his own annotated maps across Devers' desk. "They're not ambushing tanks on open roads. They're supporting infantry in towns, defending choke points, engaging from prepared positions. In every scenario, they're trading shots with enemy armor at ranges where their thin armor is irrelevant." Devers studied the maps. Red circles marked tank destroyer losses. Blue annotations showed engagement ranges and circumstances. The pattern was undeniable. Over 70% of tank destroyer casualties occurred during stationary defensive actions, not during mobile operations. Harwell continued, "The M10 weighs 29 tons. We gave it thin armor to keep it light and fast. But in actual combat, crews are welding spare track links and sandbags onto the hull for extra protection. They're adding weight anyway, slowing themselves down, and it's still not enough armor to matter." He pulled out his rejected proposal and flipped to a page of calculations. "My design weighs 37 tons, 8 tons heavier than the M10. But here's what we get for those 8 tons. Frontal armor thick enough to stop a German 88mm at 500 yards, a low profile that makes it harder to hit, and a 90mm gun that can penetrate any German tank at 2,000 yards. The revolutionary insight was simple. If tank destroyers were going to fight like tanks anyway, build them to win those fights. Don't build a light vehicle and hope crews can avoid getting hit. Build a heavy vehicle that can absorb hits and return devastating fire." Devers saw it immediately. The Army had been designing vehicles for the doctrine they wanted rather than the war they had. Harwell was proposing to design for reality. "The Ordnance Department will fight this. Tank Destroyer Command will claim you're just building another tank." Harwell nodded. "I'm building something better than a tank. Lower profile, more powerful gun, specifically designed to kill armor. It just doesn't happen to be suicidal." Devers made his decision in that moment. "You have 4 months to build a prototype. I'll handle the Ordnance Department. Make it work." It was April 1942. The invasion of Europe was already being planned. Whatever Harwell built would need to be combat-ready before American forces stormed Fortress Europe. Harwell left Aberdeen on March 20th and arrived at the Fisher Tank Division plant in Grand Blanc, Michigan, 2 days later. Fisher, a division of General Motors, was already producing M4 Shermans. Harwell needed them to build something entirely different. He assembled a team within 48 hours. Robert Grieve, Fisher's chief engineer, brought expertise in armored vehicle design. Sarah Chen, one of the few female engineers in the automotive industry, specialized in metallurgy and armor composition. Marcus Webb, a former locomotive designer, understood heavy structural engineering. And Lieutenant James Morrison, assigned by Devers as military liaison, represented the Army's operational requirements. The team gathered in the converted storage room that became their war room. Harwell laid out his core principles on a chalkboard, principles that would define everything that followed. First, the gun is everything. The vehicle would be designed around the 90mm M3 anti-aircraft gun, modified for anti-tank use. This weapon could fire a 24-pound armor-piercing shell at 2,800 feet per second, fast enough to penetrate 5 inches of armor at 1,000 yards. No German tank had frontal armor that thick. The challenge was mounting this massive gun in a turret that could traverse and depress properly. Second, slope everything. Chen advocated for sloped armor, angling the armor plates to increase effective thickness without adding weight. A 3-inch armor plate angled at 60 degrees provided protection equivalent to 6 inches of vertical plate. Soviet tank designers had proven this with the T-34. American designers had been slow to adopt the principle, but Chen was insistent. "We can't outweigh German armor," she argued. "We have to outsmart it." Third, make it invisible. Webb proposed the most radical design choice: eliminate the turret entirely. Instead of a rotating turret, the 90mm gun would mount in a limited traverse casemate built into the hull. This reduced the vehicle's height by nearly 2 feet, making it far harder to spot and hit. The trade-off was tactical flexibility. The entire vehicle would need to pivot to engage targets outside a 60-degree arc, but the survivability advantage was enormous. Fourth, use what works. Rather than designing everything from scratch, they would leverage existing components wherever possible. The transmission, engine, and suspension would come directly from the M4 Sherman. This would accelerate production and simplify logistics. Crews trained on Shermans could transition to the new vehicle quickly. Supply chains already delivering Sherman parts could support the new design without massive retooling. Morrison pushed back on the casemate design. "Doctrine requires 360-degree traverse. You're building a vehicle that can't respond to flanking attacks." Harwell's response was cold. "Doctrine also required light armor. Doctrine is killing our crews. This vehicle will kill German tanks before they can flank it. The 90mm gun has twice the effective range of anything the Germans mount. We engage first, we kill first, we survive." The team worked through the night, translating principles into specifications. By dawn on March 24th, they had preliminary drawings. The vehicle would be designated T-28, the 28th experimental tank design of the year. It would mount the most powerful gun in the American arsenal behind sloped armor that could stop anything the Germans fired. Now, they had to build it in 16 weeks. The Ordnance Department's response arrived by telegram on March 27th. Proposed T-28 design rejected, insufficient traverse capability, excessive weight compromises mobility doctrine, recommend focus on approved M10 production variants. Devers sent a telegram back the same day. "Build it anyway. I'll handle Washington." But Washington wasn't the only problem. Fisher's production floor was already operating at capacity building Shermans. Plant manager Howard Douglas made his position clear in their first meeting. "You want me to divert tooling, materials, and skilled workers from proven Sherman production to build an experimental vehicle that might not work? Every T-28 component we manufacture is a Sherman component we don't." Harwell understood the math. Fisher was producing 12 Shermans per day. The Army needed every one of them. Pulling resources for an unproven prototype seemed reckless. But he also understood that sending crews into combat in undergunned tanks was worse than reckless. It was murder. The compromise was painful. The T-28 team would work night shift, when Sherman production lines were idle. They would use rejected Sherman components, parts that failed initial inspection but were still functional. They would scrounge materials from anywhere they could find them. Chen began haunting the plant's scrapyards, identifying armor plate cutoffs that could be repurposed. Webb negotiated with tool and die makers to fabricate T-28 components during their lunch breaks. Morrison leveraged his military authority to requisition a single 990mm gun from an anti-aircraft battery. Technically theft, but no one was asking questions. The physical conditions were brutal. Michigan in April was cold and damp. The factory's heating system didn't run during night shift to conserve coal. Workers assembled prototype components while wearing heavy coats, their breath visible in the frigid air. Worse than the cold was the skepticism. Day shift workers, building Shermans that were actually going to the front lines, viewed the T-28 team with suspicion bordering on contempt. Ghost shift, they called them, playing with toys while real work happens. The criticism stung because it contained truth. Every hour spent on the T-28 was an hour not spent on proven vehicles. If the prototype failed, those hours would be wasted. Harwell felt the weight of that responsibility constantly. Technical problems emerged immediately. The 90mm gun's recoil was far more violent than calculations predicted. The first test firing, conducted in early April, cracked the mounting brackets and sent hydraulic fluid spraying across the test chamber. The team spent a week redesigning the recoil system, adding additional bracing and shock absorption. The sloped armor created assembly nightmares. Welding angled plates required precision that standard factory jigs couldn't provide. Chen and Webb designed custom fixtures, but each fixture took days to build and test. What should have been simple hull assembly became an agonizing process of measure, cut, test, adjust, and repeat. Morrison brought more bad news in mid-April. Tank Destroyer Command is formally protesting the T-28. They're arguing to Devers that it violates established doctrine and diverts resources from approved programs. Harwell looked at the half-assembled hull sitting on the factory floor, a skeleton of angled armor plates that might revolutionize armored warfare or might be dismantled for scrap. "Then we'd better make sure it works," he said quietly. The gun mounting problem consumed 3 weeks. The 90mm M3 gun had never been designed for vehicle mounting. It was an anti-aircraft weapon meant to fire upward at aircraft, not horizontally at tanks. The recoil forces in a horizontal configuration were dramatically different. Webb attacked the problem methodically. He built a test rig separate from the prototype hull, essentially a steel framework that could absorb punishment while they experimented. Through late April, they test-fired the 90mm repeatedly, measuring recoil distance, peak force, and vibration propagation. Each test provided data, each dataset revealed new problems. The breakthrough came from an unexpected source. Chen was reviewing locomotive engineering manuals, Webb's background, when she found descriptions of spring-loaded buffer systems used to absorb shock when freight cars coupled together. "What if we treat the gun like a freight car?" she proposed. "Let it move backward in a controlled way, absorbing energy through progressive resistance rather than trying to stop it dead." They redesigned the mounting with a hydraulic recoil buffer system that allowed the gun to travel backward nearly 2 feet before returning to battery. The system absorbed 80% of the recoil energy. Test firing on May 3rd produced no cracks, no leaks, no failures. The gun problem was solved. Next came the armor assembly challenge. Standard welding techniques created weak points where angled plates joined. Worse, the heat from welding warped the carefully calculated angles, reducing the effective protection. Chen spent a week experimenting with welding sequences and cooling methods. Her solution was counterintuitive: weld faster, not slower. By using higher amperage and moving quickly, she minimized heat input and reduced warping. She also specified that all welds had to be ground flush and tested with dye penetrant to ensure no cracks existed. Every weld became a potential failure point that required individual verification. The low-profile design created crew ergonomics problems that no one had anticipated. The commander, gunner, and loader had to work in a space only 4 feet high. Morrison, who would eventually command one of these vehicles in combat, physically couldn't operate the gun while wearing his standard tanker helmet. It hit the ceiling. Grieve redesigned the crew positions, offsetting them vertically so each man occupied a slightly different height plane. The gunner sat lowest, the loader stood on a raised platform, and the commander positioned himself behind and above both. It looked awkward on paper, but worked in practice. Morrison could traverse, elevate, and fire the gun, while the loader could move shells without colliding with other crew members. The transmission proved incompatible with the increased weight. The Sherman transmission could handle 33 tons reliably. The T-28, fully loaded with ammunition, weighed 38 tons. During trials in mid-May, the transmission overheated after 20 minutes of operation. Webb specified a modified gear ratio that reduced top speed from 30 miles per hour to 25, but decreased transmission load by 15%. The vehicle would be slower than a Sherman, but it would be reliable. In a tank destroyer designed to fight from prepared positions rather than racing across country, the speed reduction seemed acceptable. By late May, components were coming together. The hull was complete, the gun was mounted, the crew positions were functional. All that remained was the first integrated test, putting everything together and seeing if it actually worked. June 12, 1942. Dawn broke cold and gray over the Fisher Tank Division testing grounds. The T-28 sat silent on the concrete pad, its angular hull casting sharp shadows in the early light. Harwell hadn't slept. Neither had most of his team. Major General Devers had arrived the previous evening, accompanied by 3 skeptical colonels from Tank Destroyer Command and 2 observers from the Ordnance Department. They stood behind a protective barrier 200 yards away, notebooks ready. If the T-28 failed today, the program would be terminated. 4 months of brutal work would become a footnote in rejected designs. Morrison climbed into the commander's position. A hand-picked crew, volunteers from the base, occupied the other stations. The engine coughed, rumbled, and then settled into a steady diesel growl. Morrison's voice crackled over the radio. T-28 mobile, beginning maneuver test. The vehicle lurched forward. Despite its 38-ton weight, it accelerated smoothly, tracks gripping the dirt testing ground. Morrison guided it through a series of turns, demonstrating handling characteristics. The low profile was immediately apparent. Even at 200 yards, the T-28 seemed to disappear when positioned hull down behind the slight rise. The first firing test used solid shot against a captured German Panzer IV positioned 800 yards downrange. The 90mm gun elevated, traversed slightly left. The report was thunderous, far louder than a Sherman's 75mm. The Panzer IV shuddered as the solid shot punched completely through its frontal armor, exited the rear, and continued another 100 yards before burying itself in the earthen backstop. One of the Tank Destroyer Command colonels lowered his binoculars slowly. "Again," he said. Morrison fired twice more. Both shots penetrated. The Panzer IV's frontal armor, 70mm of steel plate, might as well have been cardboard. The 90mm gun was devastating. Then came the critical test. A captured German 88mm anti-tank gun, positioned 500 yards away, would fire at the T-28's frontal armor. This was the moment everything depended on. Chen's sloped armor design would either work or the program would end in catastrophic failure. Morrison positioned the T-28 at a slight angle, not directly facing the 88mm, but at 15 degrees, a realistic combat position. He and his crew evacuated the vehicle. Remote firing mechanisms would operate the German gun. The 88mm fired. The sound was sharp, vicious. The armor-piercing round struck the T-28's glacis plate, the sloped frontal armor, at approximately 2,700 feet per second. The impact threw up sparks and a cloud of pulverized paint. The T-28 rocked slightly on its suspension. Then, silence. Harwell ran to the vehicle, heart pounding. The armor showed a bright impact scar and a shallow gouge where the shell had struck, but no penetration. The round had deflected upward, its energy dissipated by the combination of armor thickness and slope angle. Chen examined the impact point with a measuring caliper and magnifying glass. No cracks, no spalling. The armor held completely. They fired the 88mm twice more. Both rounds deflected. The T-28's frontal armor was effectively immune to the most powerful anti-tank gun in the German arsenal at combat ranges. Devers walked to the vehicle and placed his hand on the scarred armor. "How fast can you produce these?" Harwell had been waiting for that question. First production model in 8 weeks. Full production in 6 months. Devers turned to the tank destroyer command colonels. "Gentlemen, doctrine just changed."
The official designation came through on June 20th, 1942, M36 tank destroyer. The T-28 experimental tag was dropped. This was now an approved production vehicle. Fisher Tank Division received authorization to convert 25% of their production capacity from Sherman tanks to M36s. The decision sent shockwaves through the armored warfare community. Tank Destroyer Command, overruled by direct order from Army Ground Forces Headquarters, reluctantly began updating doctrine manuals. The M36 didn't fit their light cavalry philosophy, but the combat effectiveness demonstrated at Aberdeen was irrefutable. By September 1942, the first production M36s began rolling off Fisher's assembly lines. The vehicle that had been welded together by a night shift skeleton crew was now being mass-produced. Harwell's team had solved the manufacturing challenges. The complex, sloped armor that had taken weeks to fabricate in prototype form could now be produced in 8 hours using specialized jigs and fixtures. The Army immediately sent 3 M36s to Britain for evaluation. British tank crews, veterans of North Africa's brutal armored battles, tested the vehicles at Lulworth Ranges in October 1942. Their report was enthusiastic. The M36 is the first American armored vehicle capable of meeting German heavy tanks on equal terms. The 90mm gun provides standoff capability that dramatically shifts tactical advantage. But the real test would come in combat. The 1st M36 Battalion, the 703rd Tank Destroyer Battalion, shipped to North Africa in December 1942. They arrived in Tunisia just as German forces, reinforced with Tiger tanks, were launching counterattacks against American positions. January 23, 1943, near Kasserine Pass. The 703rd engaged German armor for the first time. Lieutenant Colonel Marcus Raimi commanded the battalion from his M36. His after-action report, filed 3 days later, would become legendary in armored warfare circles. At 0820 hours, we observed 4 German tanks advancing toward our positions at approximately 1,800 yards. Positive identification, 2 Panzer IVs, 2 Tigers. We engaged from hull-down positions. First round destroyed lead Panzer IV, catastrophic ammunition detonation. Second round penetrated Tiger's frontal armor. Target immobilized, crew evacuated. Remaining enemy tanks withdrew without closing to effective range. 0 friendly casualties. The M36 performed exactly as designed. The engagement lasted less than 10 minutes. 4 American tank destroyers had stopped a German armored thrust without loss. More significantly, they had destroyed a Tiger, the supposedly invincible heavy tank that had terrorized Allied forces, from frontal aspect at range. News of the engagement spread rapidly through American and British forces. The M36 went from experimental oddity to highly sought-after asset within weeks. Unit commanders began requesting M36 battalions specifically for defensive operations and anti-armor roles. By March 1943, Fisher was producing 40 M36s per month. Additional contracts went to other manufacturers. The M36 production program expanded to include Massey Harris and Montreal Locomotive Works in Canada. By June 1943, over 300 M36s were in service across North Africa, and preparations were underway for the invasion of Italy. German intelligence captured an M36 in Tunisia in April 1943. Their technical assessment, recovered after the war, noted, "American M36 represents significant threat. 90mm gun capable of penetrating all current German armor at extended range. Frontal armor highly resistant to 88mm PaK-43. Recommend avoiding direct engagement. Use flanking tactics and indirect fire. The vehicle that had been rejected as impractical was now forcing German tactical doctrine to adapt. The M36's impact extended far beyond individual engagements. It fundamentally changed how the American Army approached armored warfare. Before the M36, American doctrine accepted that tank destroyers would suffer heavy casualties trading shots with superior German armor. The M36 inverted that equation. Now, German tanks were at disadvantage. By June 1944, as Allied forces prepared for the Normandy invasion, over 1,400 M36s were in service. They landed on Utah and Omaha beaches in the first waves, providing the heavy anti-tank capability that would prove essential in the bocage fighting. The hedgerow country of Normandy, with its narrow lanes and limited visibility, favored defensive fighting. German tanks could ambush Allied columns from concealed positions. The M36's powerful gun and heavy armor made it one of the few Allied vehicles that could survive such encounters and return effective fire. Combat reports from Normandy validated every design choice Hartwell's team had made. The low profile made M36s difficult to spot in the hedgerows. The sloped armor deflected hits that would have destroyed M10 tank destroyers. The 90mm gun could engage German armor at ranges where return fire was ineffective. M36 battalions consistently achieved kill ratios exceeding 5-to-1 against German armor. The Battle of Aricourt in September 1944 demonstrated the M36's capabilities at scale. German forces launched a major armored counterattack with over 200 Panther and Panzer IV tanks. American forces, including 3 M36-equipped tank destroyer battalions, engaged in the largest tank battle on the Western Front. Over 6 days of fighting, American forces destroyed 86 German tanks while losing only 14 M36s. The 90mm gun proved capable of penetrating Panther armor at ranges exceeding 2,000 yards, distances where German guns couldn't reliably penetrate M36 frontal armor. The transformation wasn't just tactical. The M36's success forced a philosophical shift in how military vehicles were developed. Hartwell's approach, rejecting doctrine in favor of combat reality, prioritizing survivability alongside firepower, designing for actual battlefield conditions rather than theoretical scenarios, became the new standard. Post-war analysis revealed the stark numbers. The M10 tank destroyer, designed according to pre-war doctrine, emphasizing mobility and light armor, suffered a loss rate of 9.8% per month in sustained combat. The M36, with its heavy armor and powerful gun, had a loss rate of 3.2% per month, less than one-third the casualties, despite fighting the same German forces in the same campaigns. By war's end in May 1945, American factories had produced 2,324 M36 tank destroyers. They served in every major campaign from Tunisia to Germany. Post-war, the M36 continued in service with multiple nations. French forces used M36s in Indochina. South Korean and UN forces deployed them during the Korean War, where they proved effective against Soviet-supplied T-34 tanks. Several nations operated M36s into the 1960s. Thomas Harwell received the Distinguished Service Medal in 1945 for his contributions to armored vehicle development. He returned to civilian engineering but remained a consultant to the Army's tank development programs through the 1950s. Sarah Chen became one of the first female chief engineers in the automotive industry, leading metallurgy programs at Fisher through the 1960s. Marcus Webb returned to locomotive design, but his innovative structural engineering principles influenced tank development for decades. The M36 they created together had become the benchmark against which all future tank destroyers would be measured.
The story of the M36 isn't really about tanks. It's about the courage to challenge conventional wisdom when conventional wisdom is failing. In March 1942, Thomas Harwell faced a choice that confronts every innovator. He could accept the Army's rejection and return to safe, approved work. The M10 tank destroyer was already in production. The institutional machinery was committed to a specific approach. Fighting that machinery meant risking his career, his reputation, and months of brutal work that might produce nothing. He chose to fight because he understood something profound. Doctrine exists to serve reality, not the other way around. When doctrine and reality conflict, doctrine must change. This sounds obvious in retrospect, but it's revolutionary in practice. Institutions, military, corporate, academic, develop momentum behind established approaches. That momentum creates comfort, predictability, and political safety. Challenging it requires not just different ideas, but different courage. The M36 succeeded because Harwell's team consistently asked a better question. They didn't ask, how do we build what doctrine requires? They asked, what do battlefield conditions actually demand? This reframing changed everything. It freed them from constraints that existed only in policy documents. It allowed them to design for effectiveness rather than orthodoxy. Every major breakthrough in the M36's development came from rejecting inherited assumptions. Tank destroyers must be lightly armored? Combat reports said otherwise. Anti-aircraft guns can't be vehicle-mounted? Test it and see. Sloped armor is too complex for production? Solve the production problem. Each assumption, when questioned, revealed opportunities that convention had hidden. This pattern extends far beyond military hardware. Every field has its doctrines, established approaches that everyone accepts because everyone accepts them. These doctrines often contain truth, but they also contain accumulated compromises, outdated constraints, and solutions to problems that no longer exist. Progress requires the willingness to examine doctrine critically and ask whether it still serves its purpose. The M36 also demonstrates that innovation requires building coalitions. Harwell couldn't succeed alone. He needed Devers to provide political cover. He needed Chen's metallurgical expertise. He needed Webb's structural engineering insights. He needed Morrison to understand operational requirements. He needed Fisher's production capabilities. Great innovations are almost never solo achievements. They're the result of diverse expertise united by shared conviction. Perhaps most importantly, the M36 story illustrates that rejected doesn't mean wrong. Harwell's original proposal was rejected by experts who had legitimate reasons for their skepticism. They weren't stupid or malicious. They were applying established criteria and finding the proposal lacking. But established criteria can be wrong when conditions change. The armor threat in 1942 was different from what existed when tank destroyer doctrine was written. Harwell's design was rejected based on old assumptions about old problems. When someone tells you an idea won't work, the crucial question is, won't work according to what criteria? If those criteria no longer match reality, then rejection reveals more about the criteria than the idea. The M36 went from rejected design to feared weapon because one engineer refused to accept that impossible and against doctrine were the same thing. He saw the difference between can't be done and hasn't been done. That distinction, understanding that institutional resistance isn't the same as physical impossibility, is what transforms rejected ideas into revolutionary achievements. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.